Hello, and welcome back to AP Human Geography. Today we want to talk about geologic hazards. This is going to be a two-part conversation. We're essentially talking about the geography of disaster, as I like to call it. And the first part is going to be about your geologic hazards. The second part is going to be about weather hazards, right? So first of all, let me just start with some terminology that you need to know. Please read this and be familiar with words that we are using in the class. Just a reminder as we start talking about these things. So first of all, what's a geohazard, a geologic hazard? This is any geologic event that has the potential to cause damage to property and or loss of life. And the big geohazards are going to be earthquakes, tsunamis, volcanoes, landslides, mudslides, and avalanches. Those are all in the same category, by the way. Sinkholes, and then flooding can sometimes be considered a geohazard because it occurs when water can't actually infiltrate fully into the ground. It may be saturated or impermeable or whatever. But the initial cause of flooding is usually weather related. So we're going to save our flooding conversation until we talk about weather hazards. The interesting thing about geohazards is that not only, like all hazards, do they determine where people choose to live and they have a huge impact on people, but they can actually change the Earth's surface or the internal structure of the Earth. And also, the frequency of geohazards is much more easily influenced by human activities than weather hazards are. So let's start with earthquakes. An earthquake is simply a release of pressure or stress between two tectonic plates, and that resulting slip of those plates is going to cause waves to travel through the Earth's crust, and that is what causes the shaking motion of the earthquake. You're going to find those on tectonic plate boundaries, and that can either be major boundaries or that can be in rifts of the plates or smaller fractures. It doesn't actually have to be a major plate. As a matter of fact, in the United States, I'm going to show you some examples of places where you may find earthquakes, but you're not looking at major plate boundaries. So essentially, you've got the slip of two plates at a fault line. Any kind of fault line. The other thing that causes earthquakes is volcanic eruptions, and we'll come back to that later on. I've put on all of these major info slides some links. In this case, you have a link to the Earthquake Hazards Program and a link to Earthquake Track, specifically for our area right here, which is kind of fun. All right, so when we look at an earthquake, like I said, we're having this sudden shift at a fault line where we've released this pressure. An interesting side note is that when you release pressure on one part of a plate, you build up pressure on another part of the plate. And so some earthquakes will, actually all earthquakes pretty much, will trigger other earthquakes, and so you'll have kind of this cascade effects. Sometimes you get foreshocks, sometimes you get aftershocks, and sometimes you get major earthquakes in other locations along the plate, that boundary, or maybe on the other side of the plate. So essentially you have a fault. And a fault is a fracture in rocks. It does not have to be a major plate boundary. It's just a fracture in the crust. Okay. The epicenter of an earthquake is at the surface. The focus is where the earthquake actually originates. Okay. But the epicenter is that point on the surface directly over the focus or hypocenter. Then you get seismic waves that will travel through the crust, and there are actually different kinds of waves. There are transverse waves, there are longitudinal waves, and there are circular waves. And we unfortunately are not going to talk about these, but if you were here in 5th grade, you have actually talked about them a lot. But check out this infographic, because I love me an infographic. Check this out and make sure you're familiar with it. We're going to talk a lot more about the Japan quake that it's referencing in the top corner later on in class. All right, so there are 15 major plate boundaries, and you can find earthquakes along pretty much all of these. But like I said, there are places that are not along major plate boundaries, right? This is a major plate boundary over here. But these guys are just fault lines, and we actually have earthquakes here. We have some fault lines in North Texas, and so if you'll remember a couple of years ago, we got a rash of lots and lots of earthquakes due to some deep well injection activity that caused those plates to slip. So again, it's not necessarily at major plate boundaries. You just have to have fault lines. And remember, the crust of the Earth is a little bit like a ball of glass that's held together with saran wrap that you've dropped on the floor. There'll be major cracks all the way through. There'll be little spiderweb cracks, shallower cracks, all kinds of stuff. So you can imagine the crust of the Earth like that when we talk about earthquakes. And then here I've just put some information on some major earthquakes. The really big earthquakes are typically all over 9, right, on the Richter scale, and that means that there's a huge amount of damage. You'll notice that there's no real pattern to these dates. That's generally true. And tsunamis typically compound the effect, and you get a lot higher damage and loss of life. Again, I'm going to give you an example of that in the 2011 Great Sendai earthquake of Japan, which I've actually mentioned right down here. So anyway, just here are some extras, and here are some recent earthquakes within the last 20 years. Alrighty. So your first mini quiz question is: tsunamis are caused exclusively by earthquakes. And by the way, we're going to talk about earthquakes more in class, just so you know. Are caused exclusively by earthquakes. True or false? That is actually false. Tsunamis are caused by earthquakes under the seafloor. That is definitely true. But they're just ocean waves that are generated by a sudden displacement of water. And so their geography is basically, they can be at plate boundaries where earthquakes are going to occur. So this can be oceanic, continental. That's where you get a lot of your bigger tsunamis, like the Japan tsunami. Also, fault lines underneath the water, that sort of thing. Coastlines with steep, unstable slopes, when those slide off into the water, they can cause tsunamis, including mega tsunamis. Glacial calving can do that as well. But it turns out that the tsunami itself, while those may be the areas where they're caused, they can actually affect any coastline because those waves can travel thousands of miles across the ocean. And again, we'll talk about tsunamis in class more. Oh, and volcanoes can also cause tsunamis. Yeah. And then here you get a link to the National Tsunami Warning Center. Check that out. So basically, this is how a tsunami works. You have that same situation where you have that fault line slippage, but as the fault slips up and then slams back down, it shoves all that water up, and then it comes slamming down back again, and you get water waves there. Okay, so let's talk about volcanoes. And this, by the way, is going to be just a kind of a quick overview of all of these major hazards. And again, we're going to talk more about them in class. So volcanoes, this is a vent or a fissure in the Earth's crust where you have magma. Could also be ash and gases and stuff will break through the crust and come out, right? This is typically going to be found a mountain range at either converging or diverging boundaries. And you also get hot spots on the crust. So what's happening? You've got a lot of pressure, and the magma and dissolved gases are actually lighter than the rock that surrounds them, and so they force their way through the crust. They're lighter and hotter. And it's often caused, volcanic eruptions are often triggered by the movement of plates that results in fissures or openings, or just convection currents are moving, and you've got this material moving all the time, and it shoves its way up through. Okay. Volcanoes, again, can cause earthquakes and tsunamis, and here is a link to the Volcano Hazards program. So when we look at volcanoes, there are actually different kinds of volcanoes, and we are not going to spend a lot of time talking about this, but essentially what you have is a giant magma pool, a caldera, that is underneath this mountain, and you have pressure buildup, steam, gases, whatever, and they will force their way up through this mountain, this volcano, and you can see kind of a picture of what's happening here. Please read this and be familiar with this. This is a review of whatever earth science class you have taken in the past, so I do expect you to know it. So if you have questions, please ask me. So over here, I've got two kind of the same diagram, but I like them because they show something a little bit different. So you've got volcanoes at diverging boundaries where the magma is going to well up as those plates move apart. You have hot spots where the crust is just thinner, and then you have volcanoes that are off the side of a subduction zone, a converging boundary. And here you have the plate is moving underneath the other plate, and it's dipping into the mantle, and it's going to start melting, and then that molten rock, that magma, is going to rise up here, right, through the volcano. And so you can see that in this case, the volcano is directly over the boundary. Here, the volcano is directly over the hot spot. Here, the volcano is actually not at the boundary. It's off to the side of the boundary. Okay, and then here's just the same kind of thing. And this one actually has the different kinds of volcano names on them too. So like here's a stratovolcano, here's a shield volcano. Those are just some of the different types. And of course, the products, when you're talking about the eruptions, those are different. I mean, sometimes you get molten rock, right? You get lava. Sometimes you get gases. Sometimes you get ash. But whatever you do get, volcanic eruptions are spectacular and they are dangerous, right? And so here you can see this volcanic eruption has punched through the cloud layer and essentially is punched up into the stratosphere. And you can see that flattening out. And then here you can see this has actually not had enough as much force as this, and sometimes you're talking about 3, 4, 5 miles up into the atmosphere that you're ejecting this material. That is huge. So over here you can actually see the ash and gas spreading out along the bottom of the stratosphere. So this actually goes up through the top of the up to the top of the troposphere. The other cool thing is that you have all these particles, and they're hot and they're violent. They're moving a lot. You get a lot of friction, and so a lot of volcanic eruptions actually make their own weather. In some cases, it will rain this like weird ashy rain, and there's lightning and thunder, and then you get some of your lava eruptions. A lot of your biggest eruptions are going to be gas and ash driven. It doesn't mean you don't get a lot of really dangerous lava. It's just that that's the really explosive part. Volcanoes like Hawaii or some of the Icelandic volcanoes, they erupt continually, and so they sort of just spew out lava all the time. They're super active, but they don't have the violent eruptions. It's the volcanoes that sit dormant for a really long time. Those dormant ones are the really dangerous ones. Dormant as opposed to extinct, right? Okay, so which of the following is not a possible result of volcanic eruptions? Global cooling, global warming, acid deposition, other geohazards, or all of these can be? Well, it turns out global warming is not a possible result of a volcanic eruption. I will say, though, that global cooling is, and one of the 5 mass extinctions in history, the biggest one, the one at the end of the Permian, was probably caused by massive volcanic eruptions of the Siberian traps, which caused global cooling and massive climate change. So that might be a surprise to you about volcanoes. They have a cooling effect. They also emit a lot of sulfur dioxide. And that in the atmosphere is going to become sulfuric acid, which contributes to acid rain and things like that. But it's a natural thing, so it's kind of always happened. It's not like anthropogenic acid deposition. And then we already talked about the other geohazards. So the answer here is global warming. All right, so here's just here's a list of some major volcanic eruptions, and some of these have happened maybe within your lifetime, depending on if you're a junior or senior, or maybe the year you were born. Anyway, all of these are things that had some sort of global impact. Mount Pinatubo, by the way, which was in 1991, actually caused the global temperatures to drop by about a degree, and that doesn't seem like a lot, but it's a really short time, and that's a global average. That translates to different effects in different places, actually. So unfortunately, we don't really have time in class to talk about that, but just to understand that's kind of it's a big deal. And then Krakatoa was an amazing eruption. It's actually the loudest sound that was ever recorded. It was crazy. It produced 40-meter or 140 to 150 foot tsunamis. It wiped out almost the entire island. It was amazing. And that volcano was so active after that eruption, that the volcano itself has actually grown back, right? And it's not nearly as big as it was, but Anak Krakatau actually sits in the bay over that caldera, and so this is going to happen again. And that's the thing about most volcanoes, is they'll erupt again, right? Think about Vesuvius. Vesuvius was devastating in the 79 eruption, which is the one that you're familiar with. Having said that, though, it also erupted in the 1600s and was equally as dangerous, right? And then we, of course, have our own volcanoes here. Mount St. Helens in 1980 is a very famous volcanic eruption, which resulted in not as many deaths. So there was a lot of warning for this eruption, and so people were evacuated, but there were earthquakes, there were avalanches, debris flows. I mean, it was really, really a big deal, and ash spread out for miles and miles and miles. So there was a huge impact. And then you'll notice that I try and keep all of these within the last like 1,000 years, but I put the Yellowstone eruption 640,000 years ago because it was such a huge eruption. It actually left a crater that was 30 by 45 miles across. Okay, this is huge. It's a super volcano. The caldera under Yellowstone is probably the largest caldera in the world, and it will erupt again. And when it does, it will actually affect a minimum, like immediately affect a minimum of 4 states, and over the next few days, weeks, months, the rest of the United States. It has the potential to cause climate change, all of that good stuff. So that's our own little fun secret in the middle of the country. Yay. All right, so landslides, right? Let's talk about those. And again, this is a really fast, we could spend the whole semester, we could spend the whole year on just these hazards, and that would be super exciting. But what I want you to get is just kind of a general idea of what's going on, what the potential catastrophic damage is from each of them. All right, so landslides, this is just the rapid downslope movement of material due to gravity. It's also known as mass wasting. In the case of the geography, you need a slope, right, because it's gravity driven. So unstable slopes where the earth or snow is unstable, you often find them on erosional coastlines like California. And then volcanoes also cause avalanche and mudslides, right? And so those mudslides caused by volcanoes are actually called lahars, and they're caused when the eruptions melt snow and make this big old mud field that just slams down the side of the mountain. There are some causes. Obviously, earthquakes, excess rain will cause it. Vibrations, specifically from noise, and we have a tendency to cause avalanches from that. But then the other thing that we do, this is specifically anthropogenic, is we deforest the sides of mountains. And in the 1997 floods in China, they had terraced and removed trees from lots of mountainsides, and it caused massive flooding. Like 1 million people ended up being homeless, tens of thousands of people died. So it's a really big deal, and landslides and mudslides really often associated with flooding. So I have two links for you here, the Landslide Hazards Program and the Snow and Avalanche Research Center, both USGS. And then here are just some pictures. This is actually Mount St. Helens. There's a photo of that. And this whole side, you get not only an avalanche, but you get a landslide. And by the way, when we're talking about avalanches, by the time that snow reaches the base, if it's up on a higher slope, it can actually be traveling faster than a jet plane flies. So, I mean, you're talking about a reasonable speed to reach for avalanches is like 200 miles an hour, but it can actually be going faster than that. So this is kind of big deal, right? So avalanche, landslide, the whole north face of the mountain blows off. Okay, this is an avalanche. You can see this is a town, right? So we are talking about huge events. This is a landslide that was in California, and here you have another California landslide where these houses are buried in mud. So it's real simple mechanics, but I wanted you to get kind of a visual of what the scale of what we're talking about. All right, and then sinkholes. Sinkholes are a sudden collapse of the surface into a void below, and so you need geography that is susceptible to dissolving and making cave systems and voids underneath the ground. And so you're looking for areas that have bedrock that's limestone, carbonate rock, or salt bed. because that dissolves really easily. So these caverns and spaces form as groundwater dissolves the rock, and then the surface is unsupported from below. That's the natural cause. Having said that, we cause sinkholes and stuff pretty frequently by pulling out groundwater faster than it's recharged, and also by removing oil and gas from their reserves. We can cause instability in the surface above those reserves. And so there are different kinds of sinkholes, but essentially you can get where you have a big void that forms and it actually just dissolves and dissolves and dissolves and migrates up till it meets the surface, and then whatever is on top it'll breach and then become unstable and fall in. Then the other type is where you have sort of a deeper hole, and that gets filled in over time. And so this is like the one that happens overnight, and this is more of a subsidence, happens over time. So this is a slow version. This is how you get the fast versions. Right. And then if you think that sinkholes only happen in like places where there are caves, that could be true, but here's the thing. I mean, you have to have voids underneath, but there are lots of places that could have caves, including our own area up here. Yeah, and so these are just the places where you have the diagonal lines. This is those salt beds that I was talking about. And then you've got your limestone. We have a ton of limestone here in Texas, right? Think about the Barnett Shale. That's a lot of that's all limestone where we have those great fossils coming out of. But anyway. So, also because we have coal, oil, and gas, that gives us geography that also is susceptible to sinkholes. Okay, sinkholes have the same warning indicators as volcanoes, tsunamis, earthquakes, or they have no warning. Sinkholes really have no warning if you are not already monitoring an area because you think there might be sinkholes. And even if you are monitoring it, you just know that one might form here, but there's no warning to the actual formation. It's just like there's ground and then there isn't. And here are some examples. Oh, little car driving. So sad, right? I mean, you just get these, and they can be shallow or they can be really deep, right? And it depends. And sometimes, if you're near the coast, they can be filled with water, right? This one's actually in Florida. Florida gets lots and lots of sinkholes because they have a massive underground cave system called a karst formation underneath the surface there, and so they get tons of sinkholes. Several of these are actually from Florida, and then here are a couple of others, several of which are also from Florida. And again, they vary in size. This one is one car. This one is the entire town, right? This one was a parking lot, so all these cars sunk into the parking lot. This was a house, so that's the back half of a house. So again, some are big, some are little, and some of them we actually use the cenotes in Mexico are actually sinkholes too, just as an aside. And we talked a little bit about the cenotes when we were talking about rites of passage. And we'll talk about them again when we talk about sacred spaces. So just know that cenotes are also sinkholes as we're talking about cultural stuff. Okay. So some regions have no natural hazards, but populations are too high for everyone to live there. Well, that's false, right? Everywhere has got something. The idea is that you kind of figure out a cost-benefit analysis thing and say, okay, the benefits of living here far outweigh the cost from a natural hazard, but everywhere has something. Obviously, not everywhere has major geologic hazards, but then we throw in the weather hazards, which will be the next conversation, and then you really are starting to look at nowhere is safe, but places are worth it. Yeah. So your discussion question about this, by the way, will center around what do you think are acceptable risks versus benefits in choosing a home location. All right, that's it. Thanks for listening. If you have any questions, please ask in class, and I will see you next time.